Yesterday, we started talking about Newton's second law. Okay? A couple of things we need to remember about Newton's second law. Okay, is that Newton's second law deals with situations where there is a net force, an unbalanced force, which will cause an object to do what? Not just move. Not at a constant rate, the opposite of that. It will cause it to accelerate, which is why Newton's second law is often written this way. That the net force is the mass of the object times the object's acceleration. But there is a second way to calculate that we talked about, and that is that it is also the vector sum of all forces. Okay? And we went through a couple of examples yesterday about that, and then we ended off with an elevator question, okay, which is basically a very common type, but also a very simple type of Newton's second law problem. So we ended off yesterday with the elevator that is being mentioned in question number 1 here. And that was a 600 kilogram elevator. So I'm going to see what you can remember from yesterday about Newton's second law. I would suggest by starting with a free body diagram and identifying the two forces acting on the elevator, finding a way to calculate them, and then calculating the acceleration of the elevator. All right, so the mass of the elevator is 600 kilograms, okay, and they are telling you that the cable that lifts the elevator exerts a force of 5.2 times 10 to the 3 newtons up on the elevator. Okay, we want to find the acceleration of the person. All right, give you a couple minutes on that. All right, so our first step in any Newton's second law problem is to identify the forces acting on the object in question, in this case, the elevator. Okay, we obviously have a force in the cable, or tension in this case, that's pulling upwards, and they actually go as far as to tell us how much that force is. It's 5,200 newtons. Okay, and the other force acting on the elevator is gravity. And yesterday we learned how to calculate that force. How do we do it? mg, right. Mass times the acceleration due to gravity. Now, incidentally, any force can be calculated by doing just that. We calculate gravity, the force of gravity, by going mass times the acceleration gravity produces. We can do the same with any force. The force in that cable could be calculated by taking the mass of the elevator and multiplying by the acceleration the cable would produce if it was all alone, okay, if it was the only force acting. Okay? So when we look at F net equals m times a, what we're really saying when we say it's also the vector sum of all forces is that in this situation, m times a equals mass of the, so this would be mass of the elevator times mass of the elevator times the acceleration of the cable plus mass of the elevator times acceleration due to gravity. Okay? That's really what we're saying when we say it's the vector sum of all forces. Obviously, since g is negative, this is a negative number, and we're actually subtracting. Everybody all right with that? Okay. Now, what do you notice is common to all three of these terms? Yeah, it's the same elevator. If all of those terms are being multiplied by the mass of the elevator, if I needed to, what could I do to it? Take it out. Okay? If every single one of those things is multiplied by the same number, I can take that number out. Right? And that's going to lead to something in the next question here. But basically what we're saying is that the forces and the accelerations, because they have that linear relationship, we can do a net acceleration and a net force because they work together. They're working on the same mass. All right, but back to this one here. Okay, I need to calculate the force of gravity, so I'm going to go 600 times 9.81, which will give me 5,886 newtons. So I've got 5,886 newtons pulling down. I've only got 5,200 newtons pulling up. Which way is the elevator going? Down. Okay, so now I can calculate the net force by doing the vector sum of all forces. So that'll be 5,200 plus negative 5,886, which is going to leave me with 686 newtons negative. Okay, so my net force is 686 newtons down. Can I calculate the acceleration of the elevator now? Yeah, because this equals m times a. So I'm just going to take this, take the m over here, divide both sides by m. We know it was 600 kilograms. Okay, that'll give us our acceleration, which should be 1.14 meters per second squared. Yeah. All right, everybody okay with that idea? Okay. Second question is worded a lot differently. Okay, and it can look and sound really tricky when you first start it because it doesn't seem like it gives you nearly enough information to solve. Okay, so let's have a look at question number 2 here. So I have an electric chain hoist in a garage that exerts a force of 2.85 times 10 to the 3 newtons up on an engine to remove it from a car. So is it really an elevator? Right? Anything that lifts or lowers something vertically is an elevator, regardless of whether it's actually an elevator or not. Okay? Throwing something straight up in the air is an elevator question. Okay? All right, so I've got this force upwards. Then they tell me that the acceleration of the engine is 1.50 meters per second squared up. Okay? We're looking for the mass of the engine. Everybody all right with that? Okay. So let's draw a free body diagram of this situation. Here's the engine. Okay? We don't know what its mass is. That's a little tricky. Don't know what the mass is. But I know that there's a force in the chain going up, and what other force? It's gravity pulling down. Okay. How would I calculate these forces? Well, actually, this one they tell me, right? They told me it's 2,850 newtons. Okay? How do I calculate force of gravity? Mass times gravity. Okay, well, I can't calculate it then because I don't have what? Okay? If I was going to calculate the force in this cable, what would that calculation look like? Would it look like this? Except instead of g, it would be of the cable, right? The acceleration of the cable. That would be the acceleration the cable would produce if there was no gravity. Okay? The other thing they tell me is that the engine actually accelerates at 1.50 meters per second squared up. Okay, this acceleration is happening because there is a what? We only get an acceleration if we have a what kind of force? Starts with N, short word. Net force. Okay, so what this question is saying is there's a net force. We don't know what it is, but there's a net force that's causing this acceleration here. This is the net acceleration. So when we look at this formula here for Newton's second law, okay, F net equals mass times A. But what we're really saying is the net acceleration. Okay, it's the overall acceleration of the entire system. In this case, it's the engine. Okay. Now we just said a minute ago, I drew this out on the board. We said that F net can be calculated this way, or it can be calculated by the vector sum of all forces. Well, that's gravity and the force in the hoist from the chain. Okay, we can calculate the force in the chain by going mass of the engine. So I'm going to also mention that this is the mass of the engine here times the acceleration in the chain plus the mass of the engine times the acceleration due to gravity. Okay, am I saying anything different by writing it that way? I'm still saying that m times a is the vector sum of all forces. This is how I would calculate those forces. I know a few of you are looking at that crooked because, like, put air. You're just putting up more things you don't have. You're right. Thanks. But guess what I'm going to be able to eliminate here in a second? M. Now, I should get some more crooked looks because that's what the question wants me to find. That's okay. I'm going to get to it. Okay? So, for right now, I'm actually going to take out mass of the engine because it's in every term. Okay? Every part of the equation has mass in it. So really, instead of saying F net, I could say, take out the masses, and I've got the net acceleration equals the acceleration produced by the chain plus the acceleration due to gravity. Okay? That should make sense. I mean, that's just doing vector addition. One of these forces is up, the other is down. Adding them together gives me the net acceleration of the engine. In the same way we would have done in the last unit. Okay? We would have done vector addition like that. It's collinear. It's easy. Okay? All right. Do I know the net acceleration? Yes, I do. Question told me the acceleration of the engine is 1.5 meters per second squared. So I know this number. Do I know either of these? Yeah, I know gravity is 9.81. So can I calculate the acceleration the hoist would produce?
Yeah.
How is that going to help?
Since you have acceleration, you're going to divide by f divided by a.
Right. Once I know this acceleration, I know, because the question told me earlier, the force the hoist is using. If I know the force and the acceleration, I can find mass. Okay? This is what we call the differential acceleration method. Sounds really complex, but it's really just doing vector addition with acceleration. Okay? So what I'm going to do is I'm going to solve for the acceleration that the hoist would produce if it was the only force acting. Okay? So I'm going to take the net force and I'm going to subtract the force of gravity. Or sorry, the net acceleration and subtract the acceleration due to gravity. So my net acceleration is 1.5 positive minus negative 9.81. That's going to equal the acceleration the hoist would produce if it was the only force acting. Okay? All right, so if the hoist was the only force, the engine would accelerate at 11.31 meters per second squared. Okay? Does it make sense that it should be bigger than gravity? Yeah. If it wasn't, it wouldn't be able to lift the engine out of the car. Okay? It wouldn't be more powerful than gravity. It wouldn't be able to lift it. Okay? So it can produce this acceleration, 11.31 meters per second squared. And that's up. Okay, it's positive. So now that I know that, now I can go back to this. Okay? The force that the hoist can produce is this many newtons. And I just calculated the acceleration that could cause. Now I can calculate the missing thing, which is the mass. Okay? So I'm going to go 2,850 divided by the acceleration that will produce, 11.31, and that will give me the mass of the engine. Okay, 252 kilograms. Right, so times 2.2, that's 550 pounds. Right, so if you've ever watched any of the Fast and Furious movies, there's one where like Vin Diesel grabs the chain from an engine hoist and actually holds it with one giant arm and keeps the thing from falling on a guy. No chance. Okay, if he had just reached out and grabbed that motor, he would have gone over the pulley. Okay, but taking him off like Mary Poppins. Okay, there's no way, okay, that somebody just grabs onto a chain that's holding up a half-ton engine. Okay, it's not going to happen. All right, so that might seem a little complex right now, but we're going to do a couple more like that just to kind of reinforce things here. Okay, so this is also a differential acceleration type problem. Okay, so we have a skydiver who's jumped out of a plane, okay, and they're in free fall. They haven't opened their chute yet. Okay, so during the first few seconds of the jump, with the parachute unopened, air resistance is acting on the skydiver with a force of 250 newtons. The acceleration of the skydiver during this time is 5.96 meters per second squared down. We want to calculate the mass of the skydiver. Basically the same question we just did with the engine, except with the skydiver. Okay, so we'll give you guys a few minutes. See if you can figure that one out. They've already drawn the free body diagram for you, better than I would have, because there's actually a picture of a person in here, okay, instead of a box. Right? But they've got the forces. The force of air resistance is the force of friction, and the force of gravity acting on the skydiver. Okay, let's give you a few minutes, see if you guys can come up with that one. Okay, so once again, we've got a situation where we don't get a lot of information that leads us towards getting like a net force or something like that. Okay, what we do know is that the upwards force of air resistance is 250 newtons. Okay? We don't know the mass of the skydiver, so it's going to be pretty hard to calculate the force of gravity, but that's how I would calculate it if I did have the mass of the skydiver. Okay? I would also calculate the net force on the skydiver by going mass times net acceleration. Okay? And since F net is the vector sum of all forces, it also equals the mass of the skydiver times the acceleration due to friction, or air resistance, plus mass times the acceleration due to gravity. Okay? Those are the two forces that are acting on the skydiver, and that's how I would calculate it. It's always mass times acceleration. Okay? Now, I don't have the mass of the skydiver, and it's what I'm looking for. But right now, since I don't have it, okay, I'm going to use one of the forces I do have, which is this one, okay, to calculate the mass of the skydiver. What I need in order to get that is the acceleration that this 250 newtons is producing. Okay, so let's think about it this way. If there was no air resistance, how fast would the person be falling? They would be accelerating downwards at 9.81 meters per second squared. But they're not. They're accelerating downwards at 5.96 meters per second squared. So how much of the 9.81 is being taken off by friction? Yeah, 3 point something. Yeah, okay. The difference between the acceleration due to gravity and the net acceleration, because that's what this is. This number here is the net acceleration produced by those two forces opposing each other. Right? So all I have to do is say the net acceleration, okay, equals the acceleration due to friction plus the acceleration due to gravity. If I want to get the acceleration due to friction, I'm going to subtract gravity over to this side. So I'll have A net minus G equals the acceleration due to friction. Okay, so that'll look like this. Negative 5.96, okay, minus negative 9.81. They're both down. Okay, so they're both negative. Are we all right with that? Okay. Okay, so air resistance is creating an acceleration on its own of 3.85 meters per second squared up. Okay, now that I know this number here, okay, is 3.85 meters per second squared up, and I know the force that causes it is 250 newtons, I can now calculate the mass of the skydiver by going, okay, the force of friction equals the mass of the skydiver times the acceleration due to friction, because I know this number and I know this number. Right? So force of friction divided by the acceleration due to friction equals the mass of the skydiver. 250 divided by 3.85. Right? So the skydiver has a mass of 65. Okay. Everybody all right with that? In the end, we very rarely ask a differential acceleration type problem. Okay? The purpose of showing you these is that you understand that net force is the vector sum of all forces, and that all forces are calculated by taking mass times the acceleration that force will produce. Okay? I want you guys to try question number 1 for right now, and then we'll talk about question number 2. Okay? You do not need the differential acceleration method to solve question number 1. Okay? You're just looking for her acceleration, her overall acceleration as a result of the bungee cord and gravity acting on her. Okay? I'll give you a few minutes on that. Let's have a look at this one. So I've got the bungee jumper. I'm drawing a free body diagram of the bungee jumper. I have a 55 kilogram box representing that person. Okay. There is obviously a force of gravity acting downwards on the bungee jumper. Can I calculate that? Mass times gravity. Okay, so I can calculate that right now because I've got the mass, 55, and I know the acceleration due to gravity. All right, so her force of gravity, or her weight, is 539.55 newtons. Newtons. Okay, and there's a force upwards from the bungee cord. Okay, they tell us that that force is 825 newtons upwards. That's the way I would want it if I was bungee jumping. Why? Yeah, because it's slowing me down. Okay, my net force in this situation is which way? Up. Okay, that means I'm probably not going to smash my head on the riverbed below. Okay, when I jump off the bridge, right? Provided they measured everything correctly and the bungee cord's not too long. Really research a bungee place before you choose to do it if you choose to do it. Okay, like I don't know. I won't ride in or ride Stampede because I look at the people who set them up and I go, no, I'm not trusting my life to you. Okay, think about that. You ever go bungee jumping? Do I want to trust my life to this person? Okay. All right, so we've got 825 newtons up, 539.55 newtons downwards. Okay, we can calculate our net force by doing the vector sum of all forces. Okay, so we'll have 825 plus negative 539.55. Okay, so 285.45 is our net force. And that's upwards. Can I calculate her acceleration? Yes. Take this number and divide it by what? By 55, by her mass. Okay, so the acceleration will be 285.45 divided by 55. Okay, that's a pretty typical elevator type question, okay? And I say elevator because, again, this is an object that's only moving vertically. Even though it's a bungee jumper, it's still an elevator question. It's gravity and an upward force. And that's what we always have in an elevator type question. All right, so we're looking at 5.19 or 5.2. I think we have three significant figures. Just two. The mass is 2. So we've got 5.2 meters per second squared up. Okay, so question number 2 says, during the bungee jump, the velocity of the 55-kilogram woman at the lowest point is 0. And that's not because she hits the ground. Okay, that's because the bungee cord has slowed her down until the bungee cord has stretched its maximum amount. And it's just about to do what? Shoot her back up in the air. Okay, if you've ever watched a bungee jumper, right, they fall for free fall, and then the bungee cord stretches and stretches, and then they get shot back up in the air. Okay, and then they kind of oscillate for a while until all the energy is dissipated, and then they get lowered down to the ground. Okay, so at her maximum distance from the bridge, the maximum point of stretching, her velocity is 0. Okay, compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she's accelerating due to gravity. Okay, so when she stretched that bungee cord, the maximum amount, is she accelerating?
Yes.
Yes. Okay, in fact, she's accelerating the most at that point, because the more you stretch that bungee cord, the harder the bungee cord will pull, right? Okay? When you think about it, if you take an elastic band and pull it just a little bit, it's pretty easy. You try and pull it a lot, it pulls harder and harder. The more force you put into it, the more force it exerts back. So when I've stretched that bungee cord as far as it'll go, that's where her acceleration is at its maximum, and it's in what direction? Up. Okay? And that's why she stops. Okay? If it didn't, she would plummet. Okay? So even though she's got a velocity of 0, that is actually where her acceleration is the greatest. Okay? Now, the second that that bungee cord becomes slack, her acceleration will be not just less, but it'll be 9.81 again. Okay? As soon as that bungee cord is slack, that means it can't pull anymore. The only force acting on her again will be gravity, which is why a bungee jumper typically follows a path like this, right? First they fall and they stretch and stretch and stretch, and they get shot up, and then they kind of do this. Okay? When she gets here, This is where the bungee cord is stretched the most and where it pulls the hardest. Here, the bungee cord goes slack, and she falls again due to gravity. And the bungee cord pulls and pulls, and then she gets shot back up in the air. Bungee cord goes slack, and eventually her oscillations dissipate, and she just stops, and then they can lower her down to the ground after that. All right, making some sense? All right, I'm going to give you guys about a 3-minute break here, and then we're going to look at some different kinds of Newton's second law questions. So 3 minutes, okay, and you're back here. All right, if you need to go to the bathroom, go to the bathroom. Okay, 3 minutes, you're back here. So the next kind of Newton's second law situation that we want to look at are what we call system situations. Okay, in a system, the mass is distributed into multiple parts. Okay, so instead of having just one mass, like the elevator or the skydiver or something like that, I now have two masses, but they're connected. Okay? Now, what that means is, because they're connected, they have to move together. I can't have one part of the system move and not the other. Okay? Since they're connected, that means they also have to move not just together, but at the same time and at the same rate. Okay? So if I'm looking at this diagram here, where I have a string connected to a 10 kilogram mass, and then another string, both of which are tight, okay, connected to a 20 kilogram mass, when I pull on this string, how much mass am I pulling? I'm pulling 30 kilograms. Okay? And they're both going to move, they're both going to accelerate at the same rate. If they don't, the string has to break. Or this mass has to do what to this one? It would catch up. Okay? If I continue to pull constantly, is that back mass going to catch up to the front one? No. Okay? The whole system has to accelerate as a unit at exactly the same rate. Okay? So when they show something like this, but they talk about the system, we have to understand that all parts of the system are going to have the same acceleration. The individual forces on the parts of the system might be different, but the whole system has a net force, a full mass, and one acceleration. Okay? That's what happens in a system type question. So I can simplify this situation. Okay? It says two blocks of identical material are connected by a light rope on a level surface. An applied force of 55 newtons right, okay, so this force here is 55 newtons, causes the blocks to accelerate. While in motion, the magnitude of the force of friction on the block system is 44.1 newtons. Calculate the acceleration of the blocks, plural. Okay? So, can I simplify the diagram they just drew? Yes. What would I draw instead of a 10 kilogram and a 20 kilogram block? A 30 kilogram block. Okay? This is my system diagram. The whole system has a mass of 30 kilograms. The whole system is being pulled by 55 newtons to the right and resisted by 44.1 newtons to the left. Okay? That's what I know. I can now calculate the acceleration of both blocks, or the 10 kilogram block, or the 20 kilogram block, because they're all the same. Okay. Because that's something a question might do. They might try to trick you by saying, what's the acceleration of the 10 kilogram block? And then instead of dividing by 30, you would divide by 10, and you'd get it wrong because it's not just the 10 kilogram mass that's accelerating, it's all 30. Okay? So I'm going to have here 55 minus 44.1, so that's going to be 10.9 newtons. Okay, so my net force is 10.9 newtons, and that's to the right or forward. Okay, yeah, it says right here in the question. Okay, so our vector is right. Now I've got that. Now I can find the acceleration of the system. So the acceleration will be F net divided by the mass. 10.9 newtons divided by the mass of the system. And that's what we have to remember. Anytime we have a system, when we're finding the acceleration, we're dividing by the mass of the system. Okay, always by the mass of the system as a total. Okay, that's the most common mistake made here. All right, so we got 10.9 over 30. Okay, so the acceleration of our system is 0.36 meters per second squared. Okay, all right with that. Okay, so that's how system questions start out. Then they start to get a little more intuitive, okay? Because they might start asking you to calculate forces within the system. Like, they give you this information, and then they say, the force of friction on this block only is this many newtons. What's the force in this rope? And then you would have to calculate. It's not zero. Oh, spoiler alert. That's what question number 2 is talking about. So, let's maybe try number 1 first, and then we'll look at number 2. Okay? So in question number 1, I have 2 buckets of nails hung one above the other. They're pulled up to a roof by a rope. Each bucket has a mass of 5 kilograms. The tension in the rope connecting the buckets is 60 newtons. Calculate the acceleration of the buckets, plural, both buckets. Okay? So to help you out with the diagram. That's what I know. I know that the force in the rope that connects the 2 buckets is 60 newtons. I don't know what the force on the top rope is. I know the mass of the 2 buckets. And I know the acceleration. Sorry, I don't know. I'm trying to find the acceleration of the buckets. Okay, so here's what I have to remember. The whole system is going to accelerate at the same rate, whatever it is. So sometimes, instead of finding the whole system, I can find one part of it. If I can find the acceleration of one part of the system, that's the acceleration of all parts of the system, the whole system. Okay, think about that while you're trying to figure this one out. So the trick to this question is kind of what I laid out for you a minute ago. All parts of the system are going to have the same what? Rate of acceleration. Okay? So as long as I can find the net force and the rate of acceleration of one part, I can apply that to all parts. Okay? Right now, there is no way I can do the entire system together because I don't know what the upward force on the system is. Okay? There's no way for me to calculate it, so I'm cooked if I'm using the entire system. But I do know that the bottom bucket is being pulled upwards by 60 newtons worth of force. What's pulling down on it? Gravity. Okay, so if gravity is pulling down on it, okay, I can calculate that force of gravity on the bottom bucket. Okay, I just have to go 5 times 9.81. Okay, so 49.05 newtons. Okay, can I find the net force on the bottom bucket? Yeah. Okay, so the net force on the bottom bucket is going to be 10.95 newtons. Okay, so F net will be 60 minus 49.05, which will be 10.95 newtons. Okay, that 10.95 newtons is acting on how much mass? 5 kilograms. Okay, so I can calculate the acceleration of the bottom bucket. Okay, which is going to give me 2.2 meters per second squared up. That is also the acceleration of the top bucket and the whole system, because they have to accelerate together. They're connected by a rope. Okay, they have to accelerate together. Everybody all right with that? Okay, so in the end, was the math of that one very hard? No, but it's figuring out what do I have to do in order to get there. And that's going to be the difficult part with all Newton's second law problems. Is, okay, I really have to visualize this. I have to see what kind of forces are acting. I need to see the individual masses and how they act. Hey, there's a lot of visualization and intuitive parts to these types of questions. Okay, so let's have a look at question number 2 here now. Okay, it has to do with the blocks we dealt with a minute ago. Okay, now a minute ago we calculated that the acceleration of the system was 0.36 meters per second squared. Okay, and that was to the right. Right, so we know that number in addition to all the information here. So they're saying, refer to that example, the force of friction on the 10 kilogram block is 14.7 newtons. Calculate the tension in the rope connecting the two blocks. You don't have to do B. I don't even know why they ask you B. What's the answer to B right now? What's the tension in the rope connecting the hand to the 10 kilogram block? 55 newtons. I don't know why they ask you to calculate that. They told you what it is.
Yeah.
I think it's supposed to be a typo. Okay? But I want you guys to see if you can figure out what is the tension in this rope. There's 2 ways to do it. Okay? They involve using either the 10 kilogram block or the 14 kilogram block. You can, or sorry, the 20 kilogram block. You can use either one. Okay? There's a way to calculate the tension in that rope using either block. I think using the 10 kilogram block is probably the easier way. Okay? So now you have to isolate the blocks and see if you can find what the tension in the rope connecting them is. So I would suggest to start off with drawing a free body diagram of the 10 kilogram block. So the hardest part of this is identifying the forces acting on the 10 kilogram block. Once you identify them, the solution becomes apparent very quickly. Okay? All right, give you a few minutes on that. Here's the tip I will give you. How many forces are acting on the 10 kilogram block? How many? 3. There's 55 newtons pulling forward from the hand. There's 14.1 newtons. 14.7 newtons acting backwards from friction. What else is pulling back on the 10 kilogram block? The 20 kilogram block. How is it doing that? Through what? Through the rope. Isn't that what you're supposed to find? Are you supposed to find the tension in the rope connecting them? That's the third force. It's acting backwards on the 10 kilogram block. Okay? The tension, the force in the rope. Now, do you know the acceleration of that block? Yeah. Yes, you do. You know the mass of that block. And you know there are 3 forces acting on it. You should be able to calculate the one force you don't have. I'll give you a little bit more time. See if you can get it from there. What do we call the force that this 55, the 14.7, and the force in the rope add up to? The net force. Okay? Those 3 things add up to the net force, because the net force is the vector sum of all the forces acting on that block. Everyone okay with that idea? Okay, so what we're saying then is this. Okay, F net in this situation on the 10 kilogram block equals, okay, 55 plus negative 14.7 plus the force in the rope. Okay, the vector sum of all forces. Is there another way to calculate net force? I'm multiplying 2 things together. Mass times acceleration. Do I know the acceleration? Yes. Yeah, I calculated it before. It's 0.36. Okay? We calculated it in the last question. So, if I can calculate the net force, okay, which is 0.36 times the mass, okay, which is 3.6 newtons. Everyone okay with that idea? Okay, so mass times acceleration is going to equal 55 plus negative 14.7 plus the force in the rope. This is 10 kilograms times 0.36. So 3.6 newtons equals 55 newtons plus negative 14.7 plus force in the rope. Can I calculate the force in the rope? Yeah. It's the only thing I don't know. Okay? Now, there are a lot of steps here. Mathematically, no. Intuitively, yes. Okay? There's a lot of thinking that goes into figuring out what I've got to put into this thing and put it all together. Okay? So I'm going to bring these two things over. So I'm going to have 3.6 minus 55 minus negative 14.7. That'll give me the force in the rope, which should be negative because the force in the rope is pulling backwards on the 10 kilogram block. Okay? So we're going to have 3.6 minus 55 minus negative 14.7. Okay, so the force in the rope is negative 36.7. We only have two significant figures here, so it's negative 37 newtons. Okay, everybody all right with that? Okay, there's another way to have done this question. That way would have been to use the 20 kilogram block. There's only two forces acting on the 20 kilogram block. The one we're looking for, force in the rope, and the force of friction, which is not bigger than that force. Okay, in the original question, they told us the total amount of friction was 44.1. Then they told us here that the friction on the first block is 14.7. So can I figure out how much friction is left over for the 20 kilogram block? Yeah, okay, it's the total friction minus the amount of friction that was on the other block. Okay, so 44.1 minus 14.7 will tell me this number right here. Okay, so 44.1 minus 14.7. Okay, so there's 29.4 newtons worth of friction on this block. Can I calculate the net force on this block? Do I know the acceleration of that block? Yes, 0.36 meters per second. Do I know the mass of this block? Yes. Okay, 0.36 times 20 is 7.2 newtons. All right. F net can also be calculated by the vector sum of all forces. That would be the force in the rope plus the force of friction. I now know this one and this one. Can I calculate the force in the rope? Should I get the same number I got before?
Yeah.
I better. Okay? If I don't, I really screwed up somewhere. Okay? So this will be humiliating if I'm wrong, but I'm not. Okay, so 7.2 newtons, okay, minus negative 29.4, okay, is going to give me 37 newtons. To be positive, because from the 20 kilogram block's perspective, the rope is pulling forward. Okay, on the 10 kilogram block, it was pulling backwards. Okay, are you scared? Good. Then I don't have to give you the Yoda thing where, he asks Luke if he's afraid, and he says no, and he said, you will be. Okay. Yeah, you don't have to. You're already scared. That's good. Okay. They're a little tricky, but you're gonna get the hang of it. You're gonna get better at visualizing the forces that are happening inside of a system like this. Okay? So to finish it off, yeah, I want you to try this one. Okay, is it still a system? It's two masses connected by a rope. Does the pulley matter? Not really. Okay? All the pulley is doing is making the force of gravity on one of the blocks work against the force of gravity on the other block. Okay, so really, the only forces involved in this question are the forces of gravity, or the weight of the individual blocks. Okay? So it's a system question, similar to what we just did, but actually a little bit easier. So we just said force of gravity acting on each individual box are the only two forces acting in that question. Because it does say it's a frictionless pulley. So there's no force of friction here. So those two forces are pulling against each other. If I was to let that system go, what would happen? Right, the 35 would go down, the 25 would go up. All right, figure out the rate of acceleration that they would do that at. It's not 9.81. Okay, let's have a look at this one. The thing I need to realize here is, first off, there's a couple of things. First thing is, this is a system. Okay? So all the force in the system is acting on how much mass? $60 kilograms. Okay? The whole mass of this system is 60 kilograms, 35 plus 25. Everybody okay with that? Okay, so all the forces in this system are acting on the total mass of the system. Now, these two forces, even though they're both gravity and are both acting down, are actually pulling, they're actually pulling 60 kilograms, but they're pulling against each other because the pulley is reversing it at the top. So really what I have here is this. I have a 60 kilogram mass being pulled this direction by one force of gravity and this direction by a smaller force of gravity. Agreed? Because it's a system, right? The whole system has got to move at the same rate. Okay? The 35 kilogram mass is going to drop. The 25 kilogram mass is going to go up. But they're going to do it at the same rate. It would be impossible for them to move at different rates, so one would catch the other, or the rope would break. Okay? So this first one here, we're going to have, this will be the force of gravity on the 35 kilogram mass. So we'll have 35 times 9.81. All right, so the force of gravity that way is 343.35 newtons. Okay, and the force of gravity this way is going to be 245.25. Sorry, 35.25. Okay, going this way. Everyone okay with that? All right. So, can I calculate the net force acting on the system? Yeah, it's 98.1 newtons. Okay, net, okay, will be the 343 minus the 245. I'm shortcutting here for speed. Okay, but it's 98.1 newtons. That's my net force on the 60 kilogram mass. All right. So, can I find the acceleration? Okay, 98.1 over 60 gives me the acceleration. Now, here's the thing, though, guys. The question asked on each part of the system. One part's going up. The other part's going, you would have to say that in your answer. Now, before you go, tomorrow you have a quiz. It's going to be, I'm going to give you a little tip here for one of the questions on the quiz. If I stand on a scale, okay, it tells me my what? Your weight. My weight. Well, it actually reads my mass, but it's doing that using my weight. If I'm in an elevator, and the elevator is accelerating upwards, will the scale read a bigger or smaller number? Bigger, because it's telling me how hard the floor is pushing on my feet. If the elevator is accelerating downwards, it'll read lower. So think about that. I'll post your quiz after school.
Parker, my kids are fine off.